name is Akhil Singh. My roll number is 201531031038. I am in ECD branch. Today I am going to explain four topics: Hermite polynomials, Laguerre polynomials, movement of inertial matrix, and the rocket dynamics using Lagrangian Hamiltonian mechanics. So the first topic which I am going to explain is Hermite polynomial. The Hermite polynomials are the orthogonal polynomials defined over the domain minus infinity to plus infinity with the wing function e to the power minus x square. These polynomials were discovered by Laplace but later studied in detail by Chebyshev. So the Hermite polynomial are standardized in two ways. First is the probabilist ways and second is the physicist ways. The probabilist ways define the Hermite polynomials as HEN of x, while the physicist ways of defining the Hermite polynomials is as Hn of x. Now Hen of x equals to x minus d by dx whole power n, and Hn of x equals to 2x minus d by dx whole power n. These are the two ways of defining a Hermite polynomial. Now there are various properties of Hermite polynomials, of which I am going to explain three. These three properties are: first is orthogonality. Orthogonality states that minus infinity plus infinity Hn of x into Hn of x into some w of x. This w of x equals to e to the power minus x square. So e to the power minus x square dx equals to 0 if n not equal to n. So it satisfies the orthogonality property. Second property which it satisfies is the recursion relation. Now this recursion relation is given as h n plus 1 of x equals to 2x hn of x minus hn dash of x. This is the second property satisfies. Now the third property which is satisfies is that it can be represented explicitly. Now what is the use of these Hermite polynomials? The Hermite polynomials use is that it helps in the problem, it helps in the analysis of quantum mechanical hydrogen atom. That is, the Hermite polynomial satisfies a differential equation which looks just like a Schrodinger equation. That is phi n of x double dot plus 2n plus 1 minus x square into phi n of x equals to 0. Now the Hermite polynomials satisfy the differential equation this, which looks just like a Schrodinger equation. What is this? These are not Hermite polynomials, these are the Hermite functions. That is, Hermite functions can be determined from the Hermite polynomials, and these functions are given as phi n of x equals to 2 to the power of n into n factorial into pi whole power minus 1 by 2 into e to the power x square by 2 into dn by dxn of e to the power minus x square. These are the Hermite functions, and these serve as eigenfunctions in the analysis of hydrogen model of an atom. Now the second topic which I am going to explain is the Laguerre polynomial. Now Laguerre polynomial are the solutions of the differential equation which are given as xy dot plus 1 minus x into y dot plus ny equals to 0. Now the solution of this differential equation is the Laguerre polynomial, which is given as ln of x. Now the most general way of Laguerre polynomial is xy dot dot plus 1 minus x plus alpha into y dot plus ny equals to 0. This is the most generalized way of representing a Laguerre polynomial, and the solution of this is given as ln alpha of x. This is the most general way of describing a Laguerre polynomial. Now the Laguerre polynomial satisfies various properties. I am going to elaborate on three. The first is the there comes a term of Laguerre polynomial. So it has a Laguerre polynomial comes in the multiplication theorem. Second, it satisfies the recursion relation. This recursion relation is given as x times ln of x double dot single dot equals to n times ln of x minus n times ln minus 1 of x. So this is the recursion. So this is the recursive relation the Laguerre polynomial satisfies. It also satisfies one another recursion relation, which is given as n plus 1 ln plus 1 of x equals to 2n plus 1 minus x into ln of x minus n times ln minus 1 dot of x. This is the second recursion relation it satisfies. So it satisfies two recursion relation. Also, it has third property is that its derivative. Now, the derivative property states that dk by dln of x dx to the power k equals to minus 1 to the power of k l n minus k alpha plus k x if k is less than equal to n and 0 otherwise it is 0. So it satisfies. So the derivative property of this is this, that is, it is if k is less than equal to n, this is this, but if it is k is greater than n, then the differentiation of this with k times is 0. Now, what is the use of Laguerre polynomial? Laguerre polynomial use is that it helps in the mechanical treatment of a hydrogen atom. That is, suppose we have wave function can be written as a product of spherical part and the radial part. Now, spherical part, suppose it is y into radial part rn. Now, this rn is written as e to the power minus x by 2 into x to the power of n into l to the power 2n plus 1 n minus l minus 1. That is, r and l depends upon the Laguerre polynomial. So, Laguerre polynomial helps in the mechanical treatment of a hydrogen atom. That is, Laguerre polynomial. So, if we vary n l, so if we vary the values of l, we can get different values of l, due to which we can get different values of r. So, we have different values of psi. That is, it helps in the mechanical treatment of an hydrogen atom. Now, the third topic which I am going to explain is the rocket dynamics of a rocket dynamics using Lagrangian Hamiltonian. Suppose we have a Earth, now spherical surface. Suppose Earth and rocket is moving. Now it is at a distance some q, position vector is q, and its velocity at a point is given as q dot, and mass at this instant is given as m. Now we have u equals to mgq, k equals to half m q dot square, implies that Lagrangian, which is given as k minus u equals to half m q dot square minus mgq, implies that now the Lagrangian equation is given by d by dt of dou L by dou q dot minus dou L by dou q equals to 0, implies that it is equal to d by dt of dou L by dou q dot. Now we have L equals to half m q dot square minus mgq. So d by dt of mq dot minus mg equals to 0, implies that it is equal to dm by dt, applying product rule, dm by dt into q dot plus q double dot into m plus mg equals to 0. So this is the equation of motion of rocket. Now, using Hamiltonian, we have h equals to k plus u. So we have h half times m q dot square plus mgq. Now we have minus dou t by dou t equals to dou h by dou q, implies that p equals to dou k by dou q dot equals to mq dot, and dou we have, from this equation we have minus dp by dt of mq dot equals to mq double dot plus q dot into dm by dt equals to minus mg. So this is the equation which is given by Hamiltonian analysis, and this equation is same as the Lagrangian which I proved earlier. Now the last topic which I am going to explain is the moment of inertia matrix. Suppose we have a body which has a position vector given as r, and it is revolving around its axis with a velocity omega, and we have v equals to omega cross r. We have v equals to omega cross r for a three-dimensional body rotating. Now we have L equals to sigma of I equals to 1 to n m r square omega, or since it is a continuous body, so it has a continuous mass, so the mass will be continuous, not discrete, so it will be summation m dm r cross v. As v equals to omega cross r, we have m r cross omega cross r. Now we know that a cross b cross c equals to a dot c dot b minus a dot b dot c. So we can simply write this as m times r dot r into omega minus r into omega into r into dm over integrating over the mass m. Now putting these values, now we have r for a position vector r given in a 3D, we have x I cap plus y j cap plus z k cap, and similarly omega equals to omega x I cap plus omega j k cap. Putting all these terms, in the previous equation, we get L equals to L in terms of moment of inertia, Ixx, Ixy. Now what are the values of Ixx, Ixy? The Ixx is the moment of inertia which is about x-axis. So Ixx is given as integration of n times y square plus z square times dm. Similarly for all others, Iyy and z. And Ixy is the product of the moment of inertia. It is equal to Ixyx equals to integral over m xy dm. And similarly for yz. Now the angular momentum can be written in a matrix form as Lx, Ly, Lz, This is called the moment of inertia matrix. What it tells is the distribution of mass in a body, and this is also called the tensor. And this matrix, which is called the moment of inertia matrix, Ix, this is moment of it is also a symmetric matrix. It has properties like it is a symmetric matrix, and what it tells is that how is the distribution of mass in a body.